Hey everyone! Welcome to Code of Glenn, where we build awesome tech step by step. Today, we're kicking off an exciting new project, creating a local AI-powered desktop application from scratch. No cloud services, no external dependencies, everything runs right on your machine. Imagine having your own AI assistant, chatbot, or automation tool that works offline, respects your privacy, and gives you full control over your data. Sounds cool, right? Well, by the end of this series, you'll have one built with Electron, React, LangGraph.js, MongoDB, Electron, and Ollama, all running locally. In this first video, we'll set up our project structure, install the essential dependencies, and get everything ready for development. Whether you're a beginner or an experienced dev, you'll be able to follow along and build this step by step. So, if you're excited about local AI apps, hit that like button and subscribe so you don't miss any part of this series. Let's dive in and start coding. Before we dive into the code, let's talk about what we're building and why it matters. Here are the 4 key goals of our AI desktop application. 1. Develop an AI desktop application. We're building a local AI-powered desktop app to provide an accessible, user-friendly platform tailored to specific needs. Unlike web-based solutions, a desktop app offers better security, improved performance, and offline capabilities, perfect for users who want a seamless, private experience. 2. Dependencies running on the same machine. Everything in this application, from the database to the AI model, runs locally. This means no reliance on cloud services, no latency issues, and complete control over your data. The result? A fast, reliable, and self-contained AI assistant that works anytime, anywhere. 3. Can recall conversations. A good AI assistant should remember past interactions. We'll implement conversation recall so the app can maintain context across sessions. This feature will enhance personalization, streamline workflows, and create a more natural user experience. 4. Extendable. This app isn't just a one-off project, it's built for the future. We're designing it to be extendable, meaning you'll be able to add new features, integrate with other tools, and keep up with evolving AI capabilities. Whether you want to build a chatbot, an automation assistant, or something completely different, this framework will support it. Our AI-powered desktop app is designed to run seamlessly across Mac, Windows, and Linux, ensuring cross-platform compatibility. This means no matter what operating system you're using, you can develop, run, and use the app without restrictions. To streamline dependencies and keep everything organized, we'll be using Docker, a powerful containerization tool. Docker will act as the hub for essential services, keeping everything neatly packaged and easily deployable. Inside our Docker setup, we have 2 key database technologies, MongoDB and Electron. MongoDB is our NoSQL database, perfect for handling large volumes of unstructured data efficiently. Electron, on the other hand, is a vector database optimized for neural search. This makes it ideal for AI-driven applications that require lightning-fast similarity searches. The final piece of our tech stack is Ollama, which houses our large language models, LLMs. These models bring the app to life, enabling powerful AI functionalities like natural language processing and intelligent text generation. Whether it's answering queries, generating content, or assisting users with complex tasks, Ollama ensures our app is both smart and responsive. At the core of our development stack is Electron and Node.js. These technologies provide the foundation that allows us to build a cross-platform desktop application, ensuring seamless operation on Windows, Mac OS, and Linux. With Electron's ability to combine web technologies with native desktop performance, we get the best of both worlds. To streamline the development process, we're using LangGraph.js, which acts as a reliable build agent. It helps manage application logic and workflows while providing powerful tools for AI interactions. This makes it an essential component for structuring our app efficiently. Finally, we have Express.js, which plays a crucial role in our stack. It will serve our React-based UI, ensuring a smooth user experience. Additionally, Express.js can be used to implement REST APIs if needed, enabling seamless communication between different parts of our application. With our development stack in place, we're now ready to start setting up our environment and writing the first lines of code. Let's jump right in. Let's start by creating an npm project. Set the entry point to ./dist/main.js. We'll set the project to output to this folder later. Set the type of the npm project to module. For now, let's create another project for the front end. We'll use Vite in our React application. Let's install dependencies of the front-end app and configure its build output and server settings for debugging. Let's go back to the main npm project and add Electron dependencies. Then we'll proceed with adding Electron-related code to create the main window and processes. We're going to store our Electron-related code in the Electron subfolder. Then we'll proceed with creating the main.ts, preload.ts, and renderer.ts. Imagine you're constructing a high-tech building, where every floor has a specific role. At the foundation is the main process. Think of it as the building's control center. It powers everything behind the scenes. This file manages the app's lifecycle, listens to system-level events, and creates windows where all the magic happens. For example, when your app starts up, is the architect deciding how your windows will look and behave. Now, as we move up, we reach the layer, the bridge between the ground floor and the living spaces above. It acts as a secure middleman between the main process and the renderer process, ensuring smooth communication while keeping things safe. Using tools like the carefully selects which APIs are shared, preventing the renderer from accessing sensitive or vulnerable system resources. Finally, at the top floor, we have the heart of the user experience. This is where the app's interface comes to life. It's like the beautifully designed living space where people interact with their environment. It handles all the HTML, CSS, and JavaScript that make your app visually appealing and functional. Whenever you click a button or type in a field, it's managing the interactions, sometimes talking to for support. These three layers, and work in harmony to bring your Electron app to life. Whether you're building productivity tools, games, or anything in between, understanding these components is crucial for crafting a reliable and secure application. Electron requires the preload script to be in CommonJS. So we'll configure TypeScript to compile preload.ts to CommonJS while maintaining the others as ES modules. We just created a common configuration for TypeScript. We'll proceed with creating the ES and common JS configurations by extending the common configuration. We now update package.json to add a build command for the front-end and Electron code. We'll also add another command to start the app. Let's do a quick test to see if our Electron app will load the React front-end. First, we'll start the dev npm command in our front-end React project and then open another command prompt to start our Electron app. Let's build the interface where the user can interact with the AI agent. For this, we'll use a VS Code extension called Cline to let it generate the code for us. To make it easy to write the prompt, let's write it down to Notepad first and then copy-paste this to the Cline input text box. The prompt as follows. Replace the front-end React application with an interface that represents AI interaction. Update the existing code like app.dsx and app.css whenever necessary. Use the following development stack when creating the code. TypeScript. MUI components. The user interface should include chat display area, a scrollable, visually distinct area for displaying the conversation history between the user and the AI agent. Each message should be styled to distinguish between user messages and AI responses, for example, different background colors or alignment. Input area, a text input field at the bottom of the window where the user can type their messages. A send button next to the input field to submit the user's message to the AI. Functionalities, upon pressing the send button or hitting Ctrl-Enter, the user's input should be displayed in the chat area and sent to the AI agent for processing. The application should fetch and display the AI's response in the chat display area. Styling, use CSS modules or a styled components library to style the application with a clean, modern look. Make the interface responsive for various screen sizes. When the application starts, it should display the interface right away. Now let's copy and paste the prompt to Cline and submit for it to start generating the code. Here, Cline is set to auto-approve read operations and for it to ask to proceed on other tasks. This way, we can review what Cline had done and decide if what it would do next is relevant and accurate to what we want to achieve. If its generated code isn't what we expect, we can make a follow-up prompt for it to correct its output to our desired result. A quick test to see how our user interface looks like. Before we move on to extending our code, let's set up our app's dependencies such as databases and large language models or LLM. Let's set up MongoDB. For our data to persist between restarts, let's create a volume in Docker where MongoDB will store its data. Then, attach the volume when we run the MongoDB container. Same with Qdrant. Let's create a volume and attach it to the Qdrant container. Update the restart policies of our containers to automatically start them when the machine starts. For the LLM, we need a model that supports tool calling. For this, let's choose Qwen 2.57b. We also need an embedding model to convert text into embeddings for semantic search in Qdrant. We'll use the Nomic embed text model for this. We're now moving on to developing the backend code for our application. To keep things concise, we won't go through the entire code line by line. Instead, we'll focus on discussing the architecture and various components of the backend. However, we will take a closer look at the specific sections where the front-end application integrates with the backend. To prevent the AI agent's execution from blocking other backend processes, it runs within an Electron worker thread. The AI agent utilizes two types of memory. Long-term memory, powered by Qdrant, is queried based on the latest user message, with relevant results incorporated as system messages. Meanwhile, short-term memory, known as the checkpointer, is backed by MongoDB. This memory stores previous interactions, which are retrieved and sent back to the LLM whenever a new user message is received. Before doing so, the system first determines whether the new message is still related to the ongoing conversation. If not, it summarizes the current conversation thread, stores the summary in long-term memory, and initiates a new conversation thread. We will not delve into the code details of this section. However, if you're interested in a deeper dive, feel free to leave a comment on the video. The Send Message REST API serves as a bridge between our front-end application and the back-end. It is hosted using Express, alongside the static hosting of our React front-end. However, note that in the video so far, the front-end is being hosted with Vite rather than the Express app shown in the diagram. This setup facilitates easier debugging of the front-end. Finally, the user interface component of our application runs within an Electron renderer process. This is where users engage and interact with the AI agent. Let's go and implement the changes needed in our front-end code to invoke the Send Message REST API. First, we'll install the necessary npm packages our app would need. Next, let's configure our debugger to easily trace our code when we need to. This configuration would allow us to debug both our front-end and back-end code at the same time. The main configuration is for debugging the Electron app process. This process would also spawn other threads such as rendering and the Express web server that hosts our front-end and REST API. The renderer configuration is for debugging the front-end code. This compound section of our configuration ensures that Versus code applies both the main and renderer configurations during the debug session. Let's test our debug configuration by adding breakpoints in both the front-end and back-end code to check if they get triggered. Let's create the call_graph function in the front end to trigger the LangGraph code in the back end. First, we'll define the configurations and parameters for the AI graph. We'll set the URLs for our databases, MongoDB and Qtrent, then configure the LLM and embeddings. Finally, we'll build the parameters for our fetch request to call the REST POST API. To determine the URL for the post call, we'll first check if the front end is running on the production port, 1941. During debugging, the front end is hosted on the port assigned by Vite. If it's not using the production port, we'll explicitly set the host and port to localhost 1941. We send a post fetch request to trigger the AI graph. If the call succeeds, we add the response as an AI message and include it in the messages. If the result also contains a thread we store it for use in the next call graph request. We modify handle send message to invoke the call_graph function. Let's implement our send message post API. First, we get a worker from the worker pool. We'll configure the message and error handlers for our worker process, callback functions that the worker triggers upon completing its task. If the REST call doesn't provide a system message, we establish one to ensure the LLM receives clear instructions on its intended task. We send the message to the worker, initiating its task. Verify the worker's output and provide an appropriate response to the caller. Next, we implement the call_graph function, which the worker executes. First, we establish database connections to retrieve information from the AI's memory. For long-term memory access, embeddings are required. Additionally, we obtain the LLM that our AI graph will utilize. If a thread is provided, we invoke the check and store function. This function determines whether the user's query or message is connected to the ongoing conversation within the thread. If not, it extracts notes from the conversation and stores them in long-term memory. Finally, we construct the AI graph, execute it, and return the AI's response to the caller. We proceed with updating the Electron app to establish a web server that will host both the front end and the REST API. Within the app's WhenReady callback, we invoke the function responsible for creating the web server. Additionally, we ensure the web server shuts down when the app exits. Let's test our app by launching the debugger. First, start the front end with Vite, then compile the Electron backend code. Finally, initiate the debugger. Let's enjoy a lively conversation with our AI and see where it takes us. Let's see if our AI remembers what we've talked about. Some more fun conversations. Currently, we need to start Vite for the front end to run our AI app. Let's update our code so that the front end is hosted with Express when we simply execute an npm run command. To achieve this, we determine whether the application is running in development mode. If it is, we load the URL for the web application running on Vite. Otherwise, we explicitly load the URL hosted with Express. Now, let's build the project and run the npm run command to launch our AI desktop app. To test its functionality, we'll check if it still remembers details about my dog. There you have it. We just created a desktop AI application that runs everything it needs, all locally. This setup ensures a seamless experience without relying on cloud-based services, giving you more control over your data and performance. Whether you're building something for personal use or deploying an advanced AI-driven tool, this approach keeps things efficient and secure. The source code for this application is hosted on GitHub, and you can find the link in the description below. Feel free to check it out, experiment with the code, and even contribute if you have ideas to improve it. If you found this video helpful, don't forget to like, share, and subscribe for more content like this. And if you have any questions or suggestions, drop them in the comments, we'd love to hear from you. Thanks for watching, and happy coding!